Welcome to another class about the Brown spaces, and today we'll discuss how can you get an orthogonal basis in this in the Brown space. So in the L2 of the Brown space, and such that this space also gives you an interpolation formula, just like we had in the Taylor-Wiener case. In the Taylor-Wiener case, recall that we could write any function f of z, and this you could use just Fourier inversion by you could write any function as a sum of sine or sinc functions. And this was the famous Shannon-Whittaker interpolation formula. And the way we did it, we used the characterization of the Taylor-Wiener space as a space of L2 functions with compactly supported Fourier transform. So if the Fourier transform was supported in the interval minus b, then you should use this sinc function here, and then recover your initial data. So this is for every f. Okay. And then the way we did it was to write this as the Fourier transform of the exponential. So this guy here is mapped by the Fourier transform. This function here, which should be 2 pi I in x, and then the indicator of the interval minus bb. Yes, yeah. So that was so we used the orthogonality of these ones to conclude that these functions here actually, so these guys here actually form an orthogonal basis. For the Taylor-Wiener space. Okay. Oh, and I forgot to, of course, there is the evaluation of the function, and it should be n over 2b. Yes, this is n over 2b, sorry. Of course, otherwise this doesn't make sense. So, so we recover your initial data just by evaluation, okay? And then I mentioned how important this is in signal processing. Whenever you have some kind of a signal, you can just measure it at certain discrete points. Then you can kind of recover your original signal by this formula. Okay. So we will see, what we will see today is an analog of this formula, but in a general de Bruijn space. And you will see that it's very similar, and we won't be using any kind of Fourier transforming. Here we used Fourier transform. We were going to see a proof which is Fourier transform free, so therefore it will work in general. And you'll have to do this stuff because in general, in the de Bruijn space, you don't have a Fourier transform of a kind of Fourier transform. You actually have, but I'm not going to do that in this class. But anyway, and so you need some kind of Fourier free proof. Great. So let's start. So I just want to first start with an observation. So, oops. So let's recall which the reproducing kernel is. So the reproducing kernel is KWZ equals BZ AW bar minus BW bar AZ divided by pi Z minus W bar. And this was the reproducing kernel of H2 of E. And recall you always write E as A minus IB, where A and B are real entire functions that are real on the real line. Okay, so the whole interpolation formula for the Brown space will be based in some orthogonality properties of the reproducing kernel. Okay, so suppose I have 2 points A and B in the complex plane, so that K of A and B is 0. Okay, what this is telling us? Well, we know that K is the reproducing kernel, therefore K of AB is just the inner product of KA with KB. Okay, and again, I'm using short notation. This is the short notation that I'm using. Okay, so therefore, so this is 0 if and only if Ka is orthogonal to the function Kb. Okay. So then you have a very nice thing. Whenever you have 2 points and you evaluate the reproducing kernel in there, you know that the functions, the kernel function associated with these 2 nodes, they are orthogonal. Well, this would be very useful information if the function Ka is not identically 0. It could be the case that this thing here is just identically 0, and then anything is orthogonal to the 0 function. So I have to rule out this case. And this is problem 25. So let me, 45. Let me solve problem 45 here. So what the problem 45 is that Kaa is greater than 0 exactly. So before I go to problem 45, let me just make another comment. Well, Kaa, what is Kaa? Well, Kaa is just the inner product with Ka itself. So it's the norm in the Brown space H2. And for now on, I will just put subscript 2 here, but not, this won't represent the L2 norm, it will be represent the L2, the Brown space norm, okay? So that 2 here will represent this. Okay. So if Kaa is always greater or equal to 0, okay? That's the obvious thing, nice. And it's 0 exactly when the function Ka is identically 0, okay? Which was what we were trying to investigate before, if this guy was identically 0. So the answer is problem 45. Ka is positive, and therefore the function Ka is not identically 0, exactly when A is not a real 0 of the function E. Okay? So for all A's, which are not the real 0. So recall that a function E, by being a Hermite-Piller function, put it here. It doesn't have zeros in the upper half plane. It may have zeros in the real line and also in the lower half plane, but not in the upper half plane. So in problem 45, I'm just saying, well, forget those in the lower half plane. The only problems would be the ones which are real. Okay. So because of that, is usually the case, and you see in applications that we require the function e to not have real zeros to avoid this kind of situations. Okay, so so I would like you to solve problem 45 for yourself. It is not hard to show. It's not one of the problems in the list, but because it's not that let's say enlightening. It's just a simple computation, but I will let you guys figure out. The basic reason here behind is that if you have a point, if you have a function f in the space, which has a 0 at a certain point, then you can definitely cut that 0 and the function will still belong to the space. In particular, you could show that the function, this function would belong to the space if e of w is 0. Okay, and then using this realization, let's say, you can figure out how to prove problem 45. Okay. So, okay, so now we know now we know how to decide if we have orthogonal sets, how to create an orthogonal set. Basically, what you need now is a sequence of points, A, B. Let's see, what we need is something like, let's say, a sequence of nodes, Tn, let's say, such that whenever you do Ktn Tm, that will be equal 0. Okay, so then you would have a sequence of functions, Ktn of z. These functions here would be orthogonal to each other. So you would have an orthogonal system. Okay. So how can you figure out what when we have an orthogonal system? And that is encoded in the phase function. So what is the phase function? Okay. So the phase function is usually, you will find it in the literature, be defined as f will be some kind of a real function. So that, not f phi, phase function phi, so that ei phi of x, e of x is real for all x real. Okay, so you have a function on the real, entire function on the real line is not real, you don't know the function e, but then if you just compute this argument and you cancel it by multiplying by a certain exponential, you can make it real. But the right way to do that is to define phi of z like 1 over 2i to log of e star divided by e. Okay? And you take one of the branches of the log. For instance, what you could do, you could just define phi of z as integral from 0 to z of e star over e prime of w divided by e star over e of w to w. Okay. And why this makes sense? Well, the function e doesn't have zeros in the upper half plane. On the real line, the function e star, so the function e star could have some zeros in the upper half plane. Okay, but what matters in on the real line, the zeros of these functions, of this quotient will cancel. Okay, so this function here doesn't have real zeros. That means that in the neighborhood of the real line, this function here is analytic and without zeros. Okay, so in that neighborhood, you could define this phi. Okay, so phi phi would be defined in U, which is some neighborhood of the real line, and it will be analytic there, where U is some neighborhood of R. So the picture is you have here the real line, you have here some wiggled neighborhood, and phi would be well defined in there. And because this function here has moduli 1 on the real line, it means that when you take the log, you only will have an imaginary part. So when you divide by 2i, the log, this thing will be real on the real line, okay? So, so phi star equals phi, okay? Or another way to say the phi of x is real for x real. And we see that exactly satisfy the needed property. Okay. Why satisfy the needed property? Well, you just take the explanation here on both sides, so you get like e to 2i phi e equals e star. Okay. But then if you put on the real line, that exactly means that e I phi on the real line equals e minus I phi e bar on the real line. Okay, which means that e I phi e is real. Okay, so that's the right way to do it, and you have the phase function. Okay, so one important bit about the phase function is that its derivative. Okay, its derivative will be related with a reproducing kernel. That's what I want to compute now. Yeah, so this is, so what I'm doing here is part of a problem. What's the number of this problem? Here, I think it's problem 48, maybe. Let me check here in the book. Yes, this is problem 48. So what I'm doing here is part of problem 48. Okay, so let me compute the derivative. So we have a formula for the log. We can compute the derivative easily. So that would be 1 over 2i derivative in z of e star over e minus derivative in z. And there is a, yes, that's it. That would be the derivative over a star here. So just differentiating the log. But then if you put on the real line of x, and this would be nice because this would be just the function minus, so the conjugate of the function minus itself, and you're dividing by 2i, so you can see that this is exactly just minus the imaginary part of e prime over x. Another way of writing this is the real part of I, e prime of x divided by x, e of x. I mean, when x is real, of course. And yet another way of writing this is minus a half derivative in y of the log of moduli of e star of x plus iy divided by e of x plus iy. It's a bit to the left. And this you evaluate at y equals 0. Okay, that's yet another way of computing. You just do the computation. You will see that that is true. But then, because E star is less or equal than, strictly less than E on the upper half plane, is a Hermite-Diller function. It means that when you go into the real line it means that, so you have a function which like at y equals 0, which would be, let's say this y, this is y. When you go to this direction is larger than the one going in this direction. It means that the derivative here has to be positive. Okay, so it means when you make E star over E, so this guy here has to be negative. So this thing here is greater or equal than 0 just by the fact that this is E is a Hermite-Diller. Okay. But there is a better way of seeing that this is true. There is a better explicit formula, which actually will say that phi prime of x is strictly greater than 0. So we should move this whole thing here. So this bit looks better. Okay, so what's the other formula? Well, let me recall what kxx is. So what's kxx? So K had a formula with the function E as well. So here above, I put the formula with the function A. But there was a similar one when we have E and E star. And if you use that formula and evaluate, you will see that this is exactly E of x, E prime of x bar minus E of x bar E prime of x divided by 2 pi I. Okay, x is real, of course, I'm assuming that. So if you isolate E of x squared divided by pi, what you get is 1 over 2i. So you're isolating this term and this guy here. So I have to divide by E prime bar. So you will see that you get E prime of x divided by E of x. This whole thing bar minus E prime of x divided by E of x. Okay, which again is minus the imaginary part. So, which we just computed, which is the phase function, the derivative of the phase function. Okay, so then what you get is that the derivative of the phase function is just pi kxx divided by moduli of the x squared. Okay, so if x, which is real, is not a real 0 of E, this thing here is strictly large, greater than 0. Okay, if E of x is not 0. Okay, but actually, at those points, you can still compute phi, because phi is well defined everywhere, and this will be a limit. And then you can compute that limit, and you will conclude that that point is also greater than 0. And the way to do that, the best way of doing that, instead of, because if E equals 0, it could be like a derivative of order m. Sorry, it could be a 0 of order m, so m could be very large. It could be not a good thing to do this computation exactly. But what you can do is a trick. So my claim now is, so claim is that actually phi prime of x is greater than 0 for all for all x on the real line. And how we show that? Well, suppose, well, if E has no real zeros, then it's done, because this formula here is telling us that, okay? If E has real zeros, then you can write E as some S times an E naught, where S just takes all the real zeros of E, and so therefore it will be only real entire, and therefore won't destroy the property of being Hermite-Pillar of the function E naught. So the function E naught will still be Hermite-Pillar, and no real zeros, and S real entire. And the way of constructing S is basically you use S would be just take a Weierstrass product. I don't know if I'm saying his name correctly. Okay, of the real zeros. Okay, which always converges, etc. You can just remove it. You don't care, as long as real entire, you won't destroy anything, and E naught will still belong to the Hermite-Pillar class. So therefore, the space H2 of E naught exists. And you can show that, and we can show that the map, yes, the map that goes from E naught to E, just take an F and multiply by S. This is an isometric isomorphism, okay? So this is isometric. Okay. Again, this is part of one problem. I forgot the number. Well, and then in particular, we see that, well, the functions E star over E is of course equal to E naught star over E naught, because S is real entire. So therefore, this implies that the phase function associated with the function E equals the phase function associated with the function E naught. Okay, at least in the standard way that I defined, because these functions are defined modulo adding some integer multiple of pi, of course, because whenever you take the imaginary part of the log, you have this problem, which would be equivalent of just taking a different initial point here. But if I always take 0, then there will be a predefined thing. So phi is completely defined in terms of E. And therefore, this identity here will hold. And so you can compute this derivative. That would be just the derivative of phi E naught of x. But then we have a formula. E naught doesn't have any real zeros, which will be the reproducing kernel associated with E naught, evaluated at xx divided by E naught x squared. As this E naught doesn't have any real zeros, this is strictly positive. Okay. And moreover, this bit here will also be equal to kexx divided by ex squared, when x is not a real zero of e, and in a limit sense when it is. Okay, so but this is always greater than 0. So that's the correct way of doing that. Any questions so far? Okay. So we have the phase function. What is the property of the phase function that we are looking for here? So what I want to do is a computation to tell us that. What's this computation? Okay, it's here. So observation. Suppose I have two real points, A and B. Okay. And suppose I want to make this inner product. Okay, so that would be K of AB. Okay, so let me write in terms of the function E. So that would be E of A, E of B bar minus E of A bar, E of B divided by 2 pi I A minus B. Okay, and then it's important that it's real, otherwise I would have to put bar here and bar there, and I don't want to do that. Okay. And then what we do is we isolate E of A bar, and then put E of B. Yes, so we isolate this term here. And then what we get? We get E of A divided by E of A bar, and then E of B bar divided by E of B minus 1 divided by 2 pi I A minus B. Okay, but now we have a formula for this, because in here I will use the fact that E bar divided by E, the function of x, is just e to I pi phi of x. By definition, because I define the phi to be the log of the function on the left divided by 2i. Okay, so if I use this, what we get is E of A bar, E of B, and in here we get a pretty nice formula, which would be E to I phi of B minus phi of A minus 1 divided by 2 pi I A minus B. Okay, so then we see that if A and B are not zeros of, well, if they are zeros of the function E, then these guys here are identically 0, of course. So I want to rule out that case. So suppose that E of A, E of B are not 0. Okay, suppose that they are not zeros of the function B. So then by this formula, we conclude that, so K of A is orthogonal to K of B if and only if phi of B minus phi of A, phi is congruent to phi of A mod pi. Okay, because if they are equal mod pi, that means that this is an integer multiple of pi. So this whole thing would be some 2 pi I k for some k integer. So therefore it would be 1, and we cancel with that. Okay, so I perhaps should say A different than B, of course. So I should say Okay, so that's the conclusion. So that's why the phase function is important, okay? Because if you want to take those nodes of interpolation, which would be the points we put here, and when you want these functions to be orthogonal, we have to take points which are congruent mod pi. Okay, so we conclude that, so the set, let's say K, T, N, Z, where Tn is just phi minus 1 of, let's say, some alpha plus pi n, okay, and in the integers, is a orthogonal set. Okay, and this makes sense. Well, inverting this function here makes sense because, well, the derivative of phi is always greater than 0, so therefore it's a strictly increasing function. So it would be mapping the real line into an open interval homeomorphically. So it can definitely do this. Okay, it might be the case that at some point these points here belong to the outside of the image of the function phi. So then the points Tn and stop will be just a finite number of points. So recall that the shape we have for the function phi, something like this. Some kind of increasing function. It doesn't need to cross at the origin, okay? But it's some kind of function like this. Okay. So great. So we do have the zeros. So to have the nodes. So let me make a try to see what that looks like in the Taylor-Wiener space. But before that, let me just make one more comment. So these nodes Tn when alpha, so it could select any alpha here, okay? And then I would create those nodes, because then I would create the nodes such that phi of Tn is congruent to alpha mod pi. So these, maybe I should write that. So this is the same as saying that phi of Tn is congruent to alpha. So the points that realize that. So the picture here is to take those nodes here, take those points, and this would be like the T1, this would be like the T2, and this would be like pi, and this would be like 2 pi. Okay, so these are this is how you construct those nodes. Okay, so for instance, what happens when alpha is 0? So, which was the drawing I was making anyway. When alpha is 0, well, we know that EI phi x, EX, let me write it in terms of the function a's and b. This is always real. Okay, for every x real. So when alpha is 0, that means this guy here is congruent to 0 mod pi. X, suppose that x is congruent to 0 mod pi. Therefore, this guy here would be plus or minus 1. So it would be real. So for this whole thing to be real, it means that b is 0. Okay. So, but then we have a slight problem here, because it could be the case that I am in a 0 of the function e. Okay. So I have to redo it in terms of this thing here. Okay, so let me, this for now, like assume, move this thing to the right. So just for now, assume that E of X, that E has no real zeros, okay? Okay. So if alpha is 0, okay, that means, so if X, phi of X is congruent to 0 mod pi, okay, then we just have this thing. So this thing has to be real. So since E has no real zeros, okay, it has to be a 0 of E, it has to be a 0 of B, okay? And exactly a 0 of B, because it could be, if E has real zeros, then it can also be a 0 of A. So then it could just be a 0 of B, which is also a 0 of A, a 0 of E. So I want to avoid that. So if this is 0, then if and only if B of X is 0, okay. You would be able to only conclude that if E had 0 zeros, then if that is 0, then it has to be a 0 of B. But if it's a 0 of B, you can't conclude that phi of X is congruent to 0 mod pi, because A of X could just be A of X could be just be 0, and the thing would be real as well, okay? So I wouldn't be able to go back, and I want to go back, okay? And similarly, if alpha equals pi over 2, then by the same reason, well, this guy would be purely complex, because it would be I or minus I. So therefore, it had to be a 0 of A, and you can go back if E has no real zeros. So phi of X is congruent to pi over 2 mod pi if and only if A of X is 0. Okay. So the nodes of interpolation that you're aiming for your formula would be either the zeros of A or the zeros of B. It could be something in between, but we will see that in the end, you can always like assume it's a 0 of B. But anyway, let me just mention what happens in the Paley-Wiener case. Let's say I use type pi, which means that in the Fourier transform setting, the Fourier transform is supported in the interval minus a half. So in the Paley-Wiener setting, the function Ez is just e2 minus pi I z, okay? Because then Paley-Wiener pi would be just the Brown space associated with this function, okay? So if you want the nodes of interpolation, so the set K, T and Z would be orthogonal, that would be the zeros of the function A. But this is what? This is A or B. This would be cosine pi Z minus I sine pi Z. So as nodes, we would have the zeros of the sine function, sine pi Z, which would be the integers, or we would have the zeros of cosine pi Z, and that would be the integers plus a half. But if you want to compute in general, what would be, well, what's the phase function associated with this function? Okay, we just have to do, we'll have to figure out what function we have to multiply so this thing becomes real. And obviously, I want to multiply E phi x so that this is real, and the only way to do that, there are a bunch of ways, modulo summating a multiple of integer multiple of pi, but it could just take this to be pi x. And so phi of z is just pi z. Okay, so if I want the points, that phi of x is congruent to alpha mod pi, that would be pi x congruent to alpha mod pi. Well, this would be exactly denotes x equals an integer plus maybe alpha. Yeah, x to be some k plus alpha over pi, yes. So that would be pi k plus alpha. Yes, so it should be the points. So these would be the points z plus alpha over pi, for instance. Okay, so if varying alpha, you get all the integer translations, because alpha could be anything between 0 and pi over 2, basically, or even between 0 and pi, but if you go to the other way, you get the same thing, basically. So that would be, so this would get you any translation of the integers, okay? So that's the picture in the Pavlovina space, which was the picture we were expecting, since we know that the Shannon-Whittaker interpolation formula not only works for the integers, but also for any translation of the integers. Any questions here so far? Okay. Okay, we still have like 45 minutes. So now I want to state the main theorem. And then I want to make some comments about it. This will be, I will do theorem 22, but I will do a simplified version of it. So let E belong to the mid-pillar class. Have no real zeros. In the book, the Branges do this with also real zeros. When you have real zeros, you have to take, you have some technicalities to overcome. He do that very simply, but I think in the way that it's better to understand if you explain it this way. It looks clear. The things that are going on are easy to get. Easy to understand. And let Tn be the real zeros of the function b. Okay, you can actually show that the function b doesn't have zeros on the upper half plane. Okay, and as part of the proof, we will end up showing that. And since it doesn't have zeros in the upper half plane, b being a real entire function doesn't have zeros on the lower half plane as well. So it would only have real zeros. Yes, this is just a side remark. Okay, so we know that the zeros Tn, that the zeros of b are also equal to the points phi minus 1 of pi n. Okay, and if you go to the Brown's book, and you see that he will also state it in terms of phi minus 1 of pi n plus alpha. Okay, but I will make a remark that will clarify that in a moment. So the set Z is orthogonal, well, that we already know. And the piece we don't know is that it almost spans the whole space. So if you take its span and compute its complement, that would be contained in the span of the function b itself. Okay, which is a weird statement because, well, the complement should be in the space H of E. Okay, so it should maybe like intersect this. Okay, so what I'm saying here is that it's implicit in this statement. If B is a function in the space, if B is a function in here, so then of course this span here, this would be just a span of this function, so it'll be multiples of the function B. If B is not a function in this space, therefore when I intersect, I just get a 0. And therefore the orthogonal complement of this guy is trivial, which means that this spans the whole space. So let me write that. Thus, if B is not on F2 of E, then the functions ktn of z is an orthogonal basis for H2 of E. And then we can compute the expansion of any function in that basis and also the norm of the function in that basis. So then just by applying the standard projection thing, you just project the function in each element of the basis, sum everything, and then you recover a function. The point to realize here is that if you take the inner product of f with one of these guys, you will get only f of tn. Okay, so that would make this basis an interpolation basis. And you have to divide by the squared norm of the basis, which is this tn. And therefore we can compute its true norm in the space. We just compute it term by term, and that would be exactly this. And using the formula for the phase function, and that's the formula that the Branges write in the book, using the formula for the phase function, this would be equal to okay. OTN. So I want to make some remarks. So remarks before I prove it. Remark 1. So this one I already did. This one I already did. So if I define E alpha Z as E to I alpha, where alpha is some real number, E of Z, then of course the space, I'm just multiplying by a complex number of norm 1, so I don't change anything in the definition of the space. So they are equal and isometric, and it's exactly the same space. But then you realize that if you write the second function as we always do, as a minus b, where a and alpha and b alpha real entire, you see that b alpha is the function well, I over 2 z minus alpha E star, yes, E star of z. So B alpha of x is I over 2 EI alpha E of x minus EI alpha E of x bar. And then when you can keep doing this computation, let me put this in. Let me move this guy to this bit. So then I can write E bar as I over 2 E of x e to I alpha. So that would be 1 minus e to minus 2. I mean, I'm going to use the phase function here. That's what you get. Okay, so since E, I'm assuming that E doesn't have real zeros. But instead of, I could just divide this. Okay, so that would be equal to I E alpha over 2, 1 minus alpha. So then we will see, we see that phi of x is congruent to alpha mod pi if and only if B alpha over E of x is 0. You can even put E alpha here, but anyway. So, and these would be the interpolation nodes that you want in the theorem where you can assume, where you don't need to assume that E has real zeros. Okay, but what I'm saying here, before I make this other comment, what I'm saying here is that, well, if you, by this construction, the same result works with these nodes, okay? So therefore, theorem 2 also works for the Tn to be phi minus 1 of z of alpha plus pi z. Because, well, by putting alpha here is just using the same theorem, but by multiplying your function by E alpha, which would just be a phase shift of your function. Okay. And the other remark I want to make is that a theorem, and that's what the Branges do in the book, theorem 22 also works if E has real zeros. And the way you do is exactly as I did in the first remark. You have to take the nodes as being this guy, okay? So these would coincide with the zeros of B over E, okay? So if E had no real zeros, that would be exactly the zeros of B. But since E has, you have to remove those, and it's a bit technical, you have to remove those zeros of B, which are also zeros of E, but not those with the higher multiplicity, okay? So, which would be at most one multiplicity more than this guy. So the correct thing is to take the real, the zeros of B over E. And that is what the Branges do in the book. And the functions, the interpolating functions, and you have to use key T. So it has a 0. So use this and key Tn of Z divided by Etn bar. instead of just KTN. So recall that if Tn was a zeroth E, okay, which could be the case, because it could be the case that B, it could be the case that Tn is a zero of B with one multiplicity higher than the zero of E, okay? But then this function here would be identically zero. But if you use this guy here instead, and this evaluation at the point Tn as a limit, okay, this thing here is a function in the space. It will be a function in the space. And this is, again, one of the problems in the book, to find an expression for this, even when Tn is a zero of E, okay? And then you have to use those functions here. And the conclusion of the theorem, which is this guy and this guy here, have to be understood as a limit. When Tn is a zero of E, then you have to take this as a limit, okay? And then it will be a well-defined function. And also in this formula here, okay? So, okay, so let's prove the result. The result is actually not that hard to show. We will need problem 47, I guess. And I will give some ideas how to solve it. It's a simple problem. But other than this, it's a very straightforward proof. So let me show the proof. Okay. So first of all, let's do it from scratch. From scratch, that's the expression. Yeah, do it from scratch. Stretch, that's fun. Okay, so let's just stare at the result. What do we need? We first need to show that these things are orthogonal. We kind of know that already because I did the computations. I will do it again anyway. And then we have to, let's say, take a function f, assume that it's orthogonal to all these functions here, and prove that it has to be a multiple of the function b. Okay, so that would finish basically. And these two other conclusions here, they're basically just computations. Once you know that this is a basis of the space, you just write it in terms of the basis. And then you take the L2 norm, you just take the L2 norm term by term. And this is what you get. So the only thing I have to show that this is orthogonal. And if a function is orthogonal to all these guys, then it has to be a multiple of a function b. Okay, so let me show the first part. Well, we did that already, but when you're using the zeros to function b, it's even like simpler to show. You don't need the base function, etc. So Tm and Tn out of zeros the function b, and I'm assuming that E has no zeros. Let's see if we just write the formula. What's the formula? Which is b Tn Atm bar minus btm Atn bar divided by pi Tn minus Tm. Well, that's zero, obviously, because they are different. I'm assuming they are different, of course. And Tn is different than Tm. And these guys are zero. Okay, so it's clear from the formula. We don't need the phase function, don't need anything. It's just there, visibly zero. Okay, and then you can compute also the norm squared. This is just KTN Tn. And you can even compute what this number is, and you see that it's just b prime of Tn, a of Tn divided by pi. Okay, we know that this is positive. We know that this thing is positive because E has no real zeros. Okay, great. So So therefore I know that this set is orthogonal, and therefore I can define the operator. Let me define the operator P. Let me write it first. So define PF of Z to be the sum here. Which is just the expansion of the function in the basis. Well, we yet don't know if this is equal to F. It's definitely the expansion of the projection of F in this span. So P is the projection of F in the span of these functions. Okay, so that's why I'm calling it P. And I just have to show that P of F equals F for every F. So then we have to show that P of F minus F is always some lambda times the function B. Okay, so if the function B is not in a space, the lambda would be identical, it will be 0, then P of F equals F. If B is on the space, then it is what it is. Okay. Okay, so how can we show that? And for that, we need problem 47, what is here? Okay, so to show this, I will show it in a slightly different way from the book. So if you want to prove some identity in a de Bruijn space, on any reproducing kernel Hilbert space, the only thing you need to do is to prove that the identity works for the kernel of the space, and therefore it will hold for the whole space. Okay, so because, well, let me make that comment. Since the span over all w's in the complex plane of these functions, kw, okay, so let me write it like this, kw. So it's a function of z. If I expand, if you do linear combination for this function, this is dense in H2 of E. Okay, and why it is dense? Because, well, suppose that you have a function which is orthogonal to all these guys. Okay, well, the inner product with against one of these guys is just F at W. So it means that F at W is 0 for all W's in the complex plane. Therefore, F is 0. And from this, you can also see that, well, I even don't need all the complex numbers here. I could just take a subset of the complex plane, which has an accumulation point in the complex plane. And then by the standard results we see in complex analysis, if F would be 0 at those points, F would be identically 0. Okay, so this is even an overkill. So since this span is dense, so if I prove, so I only need to show the P of KW minus KW is some multiple of B. Okay, if I do this, then by a limiting procedure, I can just do linear combinations. So that would be like a lambda, which would depend on W. So then we can do some linear combinations, let's say, like this, conversion to F in the norm. Well, a projection operator is always bounded. The norm of the projection operator is always less than or equal to 1. So therefore, this identity here will be true in the limit. So therefore, P of f minus f will be what? The limit, let me call this f, it's a j from 1 to capital N. So this would be the limit of Pfn minus Fn, which is converging not only in the space, but also uniformly in compact sets. But that would be the limit of this times the function b. So since this is converging, okay, in the space, again, convergence in the space, recall that convergence in the space, in the norm of the space, implies convergence, uniform convergence in compact sets, because the evaluation functional is bounded, okay? And the evaluation functional is bounded, and it's bounded by the norm, it's KWW, okay? And KWW is a continuous function, therefore bounded in compact sets. So since the evaluation function is bounded and uniformly bounded in some compact sets, when you vary W in a compact set, then convergence in the space implies convergence, uniform convergence in compact sets. So this limit here also works uniformly in compact sets on the complex plane. Okay, so this is converging. So therefore this limit, whatever it is, I don't care, it is convergent to a number. So this thing, so but this everything is multiplied by b of z. So let me put b of z here, just to be completely clear. So that would be some other lambda, which I don't know what it is, b of z. Okay. So the only thing I need to show is this identity here. Okay. Any questions in this argument here? Okay, so, and for that we need problem 47. Okay, so let me state what problem 47 is. We are almost done, and this thing here will follow by a very simple application of problem 47. So what's problem 47? Let f, suppose you have some nodes, which I will use the same letter because these will be the nodes anyway. Real nodes, Tn, and you have a function which is analytic in this outside these nodes. So the Tn is a real. So analytic. I will assume that f star equals f. So on the real line is real, and I will assume that the real part of minus if is greater than 0. Okay. In the upper half plane. Okay. Then there exists p greater or equal to 0. There exists pn greater or equal to 0, so that f of z minus f of w bar divided by z minus w bar equals p plus the sum of pn divided by t n minus z and tn minus w bar. And pn here, let me move this to the left. And pn here will be the limit. Let me write this here. Pn is the limit of z minus tn, f of z, and z converges to tn. And convergence is uniform and absolutely away from the nodes. Absolutely, let me see what I should say. For Z and W bar, away, so far away from the TNs. That means if I put the moduli here inside and I take the tail of the sum and take the soup of this tail in a set which has a positive distance from the points Tn, then this thing will converge. Okay? And we will have this formula. Okay? Wait, and we can even put here like, because it's finite. Okay. So since this is finite, it's easy to conclude uniform and absolute convergence away from the nodes. Okay, so I just have to prove that this is finite, and I have to prove some kind of representation. So the solution is actually quite easy because, well, because something has positive real part, I just apply Poisson by Poisson representation. We know that f of z is a minus I f of z, because that's the thing. It should be minus I zp from some p positive, ic from some c real, plus 1 over pi I integral of 1 plus tz divided by t minus z, the mu of t 1 plus t squared for some function, for some known decreasing function. Okay, and we know that the integral is finite. Okay, that's Poisson representation. And then when we take from that, well, that's this is basically equal to one of the problems. But what you have to realize is, since that f is real on the real line, if I evaluate this function here on the real line, it's 0. If I take the real part of this, if I take the real part of the function of the real line, is 0, because f would be real and multiplying by multiplying by I, and you take the real part, that would be 0. Okay, so so we do know by Poisson representation that the integral from a to b would be the limit when y goes to 0, and this would work if a be a point of continuity of the function mu. So that thing will be what? That thing would be exactly the integral of the real part of minus I f of x dx. And this is if, well, if let's say I have an a and a b between 2 points, let's say 2 consecutive points. If I have 2 consecutive points and pick a and b inside, well, this limit here would definitely converge because the function is analytic there and converges to this value, but this is 0 because the function is real on the real line. Okay, so this shows that the measure mu is 0 between 2 nodes, or in other words, the function, non-decreasing function mu is constant between 2 nodes. So therefore, it only jumps, possibly jumps at these points Tn. So from that, you conclude that the measure mu is simply a sum with some values Pn, which I will multiply by pi here, and some deltas at the point Tn. Okay. Because between these nodes, the function mu is constant, so the measure is 0. So it has to be that. Great. So if you go back and write the Poisson representation formula, if you go back in here, then you get the very nice formula. And that you just write what it is, and this is just 1 plus Tn of z divided by Tn minus z, and this would be like pi Tn divided by 1 plus Tn squared. And I put this pi here, so this pi cancels with this guy here. And I can also multiply everything by I, so to cancel this and this. So let me do that already. So I multiply everything by I. So this would be minus C. And this will go away. And we have this pi here, which I will cancel with this guy. So we get this clean formula. And then if I do the Newton quotient, the C goes away, and we have just P here. And you can do this Newton quotient to the other part, and you will get exactly what the formula claims. Okay, and that finishes the proof. It basically finishes the proof because if we go back, the only other thing that I needed was this representation here of the PNs, but this is easy because if you multiply both sides here by Z minus, shouldn't be Tn minus Z, should Tn minus Z. Let me see if I'm writing the formula in the right way. It should be completely equal to the book. Yes, it is Tn minus Z, of course. So, yeah. So, so if you just multiply Tn minus Z here on both sides, and you take the limit when Z goes to Tn, and you take W any other point in, let's say, in the upper half plane, and say W equals I, for instance. So this bit in the thing would go away, and you only have like Tn minus W bar here. And on this bit, you will cancel this Tn minus Z, and you will have, again, this Tn minus W bar. And the only one that will survive would be the particular Tn you took here. So you only have one term, and with this cancellation, you have exactly this guy. And this guy will also go away because you multiply by Tn minus Z and taking Z to Tn. Okay. So this here, what I'm saying that this here can be easily deduced from this formula here. And the PNs have to be greater or equal than 0 because the function is mu is greater or equal than 0. So the jumps have to be greater or equal than 0. Okay, so this finishes the problem. Okay, any questions in the solution of this problem? Okay, so let me go back to the theorem. So what we needed to show was that this is true for every W. Okay, and this would be a straightforward application of the result of the problem. So applying problem 47 to, and what's the function I need to apply this problem? To this guy here, f equals minus a over b. So I'm claiming that this function that is the real part of I A over B is positive in C plus, okay? I'm claiming that, okay? Let me prove that in the end. Let me just assume that it is the case, okay? So then I can apply the result to this function, so the problem. And what would be the nodes that F won't be analytic? Would be exactly the zeros of B, okay, exactly. So if I apply the theorem to this guy, I get that A over B of C minus A over B of W divided by C minus W should be equal to a certain P plus a sum oh, this would be bar, sorry. Yeah, and it should be a minus here. It should be a minus there. Yes, and plus here, sorry. And then it should be a Pn here, and then a Tn minus Z, and a Tn minus W bar here. Okay, and we know what the Pn's are. The Pn's are the limit of F times Tn minus Z. So the Pn's, let me recall, Pn is the limit, Z goes to Tn of Tn minus Z, F of Z, which the way we defined is exactly just E of Tn divided by B prime of Tn. Okay. So let me rewrite this. This is just E of Tn divided by B prime of Tn. And for some number B. And then if I multiply, if you just multiply by B of Z, B bar, B of W bar, those sides, in the left-hand side, and you divide by pi, then you get exactly the reproducing cardinal on the left. And on the right, you get P over pi, P of Z, P of W bar, and in here plus, and what you get is A of Tn divided by pi, B prime of Tn, and then you get B of Z divided by Z minus Tn, and then B of W bar divided by, yeah, I can switch both of these guys if I want. I'm switching it. You can switch this, okay? And if you do the calculation, it's not, it's easy to write this in another form. This is exactly KWTN, KTN of Z, KTN, Tn, and this bit here is exactly P of KW. Okay, so you conclude that P, let's say that KW minus P of KW equals some lambda, which would be this P over pi here, BW bar, and then P of Z. Okay, which was exactly what we wanted to show. Even more, we even computed the shape of the constant, which would depend on W. So the constant that multiplies B is this guy. Okay, so that would finish the result. So it was a direct, so this was just a simple application of the Poisson representation. Now I just have to show this claim here. Okay, so this finishes the proof mod star. Okay, and for a star, and to prove star, we'll just use the fact that KZZ is always, if Z is in the upper half plane, this is always positive, because this would be zero only if you had real zeros of E, which I'm assuming it's, you don't. And then you just write what this thing is. Oh, sorry, this won't be that. This would be just PZ A of Z bar minus P of Z bar A of Z divided by pi Z minus Z bar, which in the upper half plane, you will get what? The computation, I did this at some place here. 5, 6. Yes, this is just, okay, so you just isolate this bit and isolate this bit, okay, and then you put also, oh, and this part here is just pi 2 pi I y if z equals x plus iy. So we can just isolate pi y here. And then what it will get is what is, so there is a 2i here, and in here would be a divided by b bar minus a divided by b. Okay, and that is the real part of I A over B, isn't it? Yes, because this would be the imaginary part minus the imaginary part of this guy, which is the real part of I times this guy. Okay, which was exactly what we wanted to show. That the real part of I, this guy is positive, and we know that this whole thing is positive, and y is positive, so therefore real part of IAB is greater than 0. Okay, so that would finish. Okay, any questions here? Okay, great. So this is a very nice, one of the very nice results in the Branches space, because you have this orthogonal basis, easy to build, coming directly from the reproducing kernel, and mimics the Paley-Wiener case. And this is very nice in the sense that it's a very nice generalization and very useful in applications. And we probably will see one of these applications in number theory, where we have to estimate a certain integral, and we have to use that. We have to use this thing here, the Poincaré. I think this is called Poincaré. What's the result? Yes. This is yes, this is the theorem. Well, we have to use this formula here to estimate L2 norms. Okay. And I hope you enjoyed this class, and see you next Tuesday. Bye-bye.